Okay, hello everyone. My name is Nick, and I'm going to be telling you about a couple of works. This was a merged talk related to using the idea of low energy assumptions in quantum simulation to get a speed up. There are many authors involved in this, and we've been working on this for quite a while. I think Rubin and I were discussing this actually at the last QSim in Telluride. The idea is a combination of two things, sum of squares representations of Hamiltonians and spectral amplification. I'll explain what each of those are, and so you'll hear me refer to this as SOSA, an acronym that comes from the merging of the two. So the nice thing about SOSA is that we've gotten chemistry for ground state energy estimation down to hours. And so the natural place to exploit low energy assumptions is in ground state energy estimation. You're at one end of the spectrum. To explain this, I have this nice sort of progress in gate complexity over the years for this task. And so what's shown in this plot is the gate complexity in terms of highly expensive resource states like Toffoli gates as a function of time. Each of the dots is an algorithmic paper that improves on prior results by factors of 2 to 4, and SOSA is all the way on the right here, which is quite nice. This is for a second quantized representation of the molecule shown here on the slide, and this is for one run of quantum phase estimation. And so the really nice thing that's sort of not shown in this plot is that SOSA is a new direction in terms of ideas in which we can continue to improve these and optimize these algorithms. So that's really exciting thing about this work. So before I get into the idea of SOSA, I need to explain a little bit of background for everyone, and that's the LCU framework and QPE. So a Hamiltonian has a linear combination representation if it can be represented as a weighted sum of unitaries. And there are circuits to construct what is known as a block encoding, which is a unitary that puts that Hamiltonian in the top left block of that matrix that's been appropriately rescaled. So using those circuits that construct this block encoding, we can construct yet another unitary called the walk operator that dictates the dynamics in subspaces corresponding to the arc cosine of the Hamiltonian. And so we can perform phase estimation on that walk operator and learn phases, and then by error propagation, back out precisely how many queries to the controlled walk operator that we need to estimate our original eigenvalues to fixed precision epsilon. And so that's the query cost that we're going to work with. But what I was showing on the previous slide are gate complexities. And so to get the gate complexity, you need to compile the block encoding and multiply that by the query costs. And so we're concerned ultimately with this cost expression down at the bottom, namely how many resources we're going to need in terms of the total gates. So with that out of the way, I can explain the idea of spectrum amplification. This goes back to Rolando Soma and Sergio Boschwa in 2013. That was used in adiabatic quantum computation, or to speed up adiabatic quantum computation. And the idea can be seen in a sort of a toy example. Let's say you want to estimate x, but you're given random variables related to the square root of that value. And you can ask, to what precision do I need to measure the square root to get a constant precision in x, that red variable? And that's what's shown graphically here and in the expression or in the equation down at the bottom there. And what we need, what's shown is that as you approach 0 here, you can tolerate a much larger precision, which is quantified by this blue line for a constant precision in x. Another way to say that is that you can exploit the steepness of the derivative of the function that you're interested in estimating if you're careful. And so this is an example where error propagation is actually helping you. So how do we translate that to a Hamiltonian setting? So we can directly translate this toy problem into something that maybe looks a little bit more quantum, but is maybe a little farther from reality first. Let's just say I give you a Hamiltonian that has some natural square root. H square root here is some norm 1 operator times some positive scalar lambda. And let's say I give you a block encoding of that. Well, we were discussing on the previous slide, you can do some type of singular value estimation here. And I know from those queries, that query complexity, in order to measure the eigenvalues of my original Hamiltonian to fixed precision, I'm going to need something that scales as the square root of the ground state energy times the block encoding LCU lambda divided by epsilon. So this, of course, is lower than the standard approach if my square root E times lambda is smaller in this case, if the block encoding costs are the same. So again, this is a simple propagation of error from going from the phase estimating some function of my original Hamiltonian and then backing out exactly what my desired thing is, which is the eigenvalues of my original Hamiltonian. Okay, so there's how do I go back? There's a couple of problems with this. This Hamiltonian is not something that you see every day in nature. This is not exactly what you are usually given as a Hamiltonian simulation problem, or represents a particular class of things that might be interesting to look at in chemistry or condensed matter. It might not be easy to do singular value estimation, and SOSA really sort of fixes up a bunch of these issues. Okay, so let's look at something now that looks a little bit more familiar. I'm going to give you a Hamiltonian that's a linear combination of Pauli strings. This is already in LCU form. And I'm going to try to do what I did on the previous slide in the most naive way possible. So I'm going to first take each of the terms in my linear combination of unitaries here and convert that to something where I can square it to the original Hamiltonian. And I do that by taking each Pauli term and turning it into a projector by subtracting a constant. I'm going to collect all of those terms into a large rectangular matrix. And the nice property of this is that if I square that rectangular matrix, it exactly equals the shifted, or the Hamiltonian shifted by the constant, which in this case is the LCU1 norm. Okay, so using the infrastructure that I just introduced on the previous slide, then I know that my query complexity to estimate the eigenvalues of my original Hamiltonian, which is just this sum of weighted Pauli operators, goes as delta times lambda LCU square rooted. And this can be very, very large. The problem here is that what I've done is I've shifted by such a large amount to make the equality hold. Oh, there's no laser pointer, that's okay. Such that there's no states that lie in the low energy space that I can exploit this error propagation that spectrum amplification uses to give us an advantage. So I need to do something a little bit more clever. I can't just naively form a sum of squares representation. Okay, so a better strategy would be to actually variationally optimize the sum of squares representation. It turns out that any Hamiltonian can be written in the form that I have here in the first line. H plus some constant beta is equal to some sum of squares operators. I can choose some ansatz for those sum of squares operators bj and optimize or maximize beta, the lower bound in this case. And it turns out that that mathematical program has a very nice structure. It's a semi-definite program, which is efficient to solve as long as the ansatz size for bj's are polynomial in the system size. So just like on the last slide, I can take each of these bj's, form them into a large rectangular matrix such that the equality of the Hamiltonian plus some constant is equal to the sum of squares, and perform the same protocol of singular value estimation and then error propagation. So this works now because my lower bound beta is much closer to the ground state energy, namely the gap delta, the ground state energy of sum of squares. It's much, much smaller, and there are states in the low energy space here that can use the spectrum amplification fortuitous error propagation. The nice thing about this is this sum of squares problem is actually the dual to something that we do in quantum chemistry called the n-representability problem. That's where you optimize over the moments of some distribution. And so we have a lot of knowledge about actually how to design these ansatz such that they provide good lower bounds. Okay, so that is a nice sort of theoretical motivation, but we're really interested in gate costs and whether this idea sort of holds asymptotically. And so one thing that Robbie did, which was really sort of set us on this path that leads to these state-of-the-art chemistry simulations, is he looked at the SYK example and found an asymptotic advantage in system size. So the SYK Hamiltonian is a quartic-Majorana Hamiltonian where the coefficients are all Gaussian distributed. And what you can do is go through this protocol that I was showing on the previous slide, where you can construct a nice sum of squares representation and optimize the lower bound beta. This gives you a SOSA, a square root Hamiltonian, to form into a large rectangular matrix and then perform singular value estimation. And now in this case, you can prove that the lower bound actually scales with system size n. So you might think, well, that's pretty large. But if you propagate this with spectrum amplification for estimating the eigenvalues of SYK, you actually get an asymptotic advantage with respect to just naive LCU gate complexities here. And so that's a really nice motivation that in strongly correlated fermionic systems, we can get an advantage. I should say, actually, one of the important things here is that you might expect, well, maybe I want to increase the size of my algebra and make this lower bound beta better and better and better. And that would indeed improve the query complexity. Generically, as I improve or I increase the size of my algebra that I'm using to represent the sum of squares, my lower bound will improve. But we're interested in total gate complexities. The problem there is that as you improve the lower bound by increasing the size of your algebra, or the four ansatz you have, the many-body rank of the ansatz you have for the BJs, you are increasing the total gate complexity because the block encoding cost of that object is going up. And so there's a special sort of trade-off you have to look at here. And in this case, if you actually go to level 3 algebra, namely BJs are spanning triplets in Majoranas, you actually lose this speed up. So in the chemistry setting, what we're going to need to do is find a good trade-off between the form of the sum of squares algebra, the lower bound, and a block encoding cost. And so the chemistry Hamiltonian can generically be written like this quartic operator in ladder operators that I have up here on the top. And I'm going to do the most naive thing and take the simplest algebra possible to represent that Hamiltonian. I actually used to work in lower bound methods in chemistry, and so I know that using for sort of the full quadratic algebra, you can get very, very accurate solutions. Namely, beta is very close to the ground state energy, usually like 0.01 in the units of the problem. But here, what we're going to do is use a much more sparsified form of the algebra. This is actually a subcomponent of all of the quadratic ladder operators that we want, that you might imagine expecting at the full level 2. And so we need to quantify whether spectrum amplification works here. And to do that, we're going to run through the protocol that I was showing before. Select an algebra, optimize all of the coefficients, C, D, E, and G, while maximizing beta in a semi-definite program, get lower bounds, and then I need to get a bound for the upper bound, so I'm going to use a variational wave function there. And in this case, we're looking at a variety of chemical systems that have been used as benchmarks for quantum algorithms over the years. My upper bounds are computed by some wave function ansatz, like modest bond dimension DMRG, and the lower bounds are computed with this sum of squares ansatz that I have here. What's shown in ESOS is exactly this gap, this delta between the lower bound and the upper bound. And so those are actually quite large in the units of the problem. These are 1 Hartree, the sort of accuracies that Birgitta was talking about in the previous talk are around 1e minus 3. And so we're pretty far from that. Namely, this sum of squares ansatz is quite bad for chemistry, but it's good enough for spectral amplification. Namely, the effective lambda that we get, which is that last column on the right-hand side, is lower than what you might expect by just generically block encoding and applying and estimating the eigenvalues. And so what that's sort of showing is that we don't need super tight lower bounds. Again, we're playing this trade-off between the tightness of the lower bound and the block encoding cost. And that's something that we really have to optimize for this method to work and to employ spectrum amplification. So one thing that we do to optimize further is we can layer on all of the advancements that I was showing on the first slide of this talk. Each of those dots was some algorithmic improvement in ground state energy estimation. And we can layer those on top of SOSA, which is a really nice property. We developed a new tensor factorization. The technical details of this aren't really that important for this talk. The important thing is that we can combine those together with SOSA to get a bigger improvement. And combining all of these things together, we can see sometimes very, very large factor improvements relative to the best algorithms for each of these benchmark chemical systems that we were looking at. And so this is really the complementary data to the first slide, showing that if you are very careful about your sum of squares representation and optimizing the block encoding cost and the lower bound and layering it on top of the existing algorithmic primitives that exist to give speedups, you can get very, very large improvements in ground state energy estimation. So you might imagine that this lower bound, or this low energy assumption doesn't hold just for phase estimating ground states. There's actually a number of areas where we can apply this. And indeed, that ends up being the case. Whenever you have this low energy assumption, there's a handful of algorithms that you can transfer over these ideas to, expectation value estimation and time evolution as well. And you can make this sort of like correspondence table where effectively, if you're costing things out within block encodings, you have this transfer between lambda cost to lambda, the square root of lambda times delta, which is that energy gap that we're interested in. And so that's a very nice thing that we can sort of now use in a lot of these chemistry examples where we're looking at low energy states. OK, so I'm going to try to finish up there. So SOSA was this trade-off now between the lower bound, the quality of our lower bounds and the cost of the block encoding. And what we did here was really the first step. We didn't optimize too much on the sum of squares representation. You can imagine, for example, trying to improve that by maybe making bespoke representations for particular systems that have low block encoding cost. You can imagine other improvements to the algorithms in that way. I should mention also it's naively applicable to tomography in a low energy setting. You can do this in a coherent and an incoherent setting. Really the way that this works is that you just get a much tighter variance bound when you're in the low energy setting. This is sort of a sort of known result for positive operators. SOSA involves a polynomial time pre-processing. I'm not solving some complicated QMA complete and representability problem before. I can tolerate a bad approximation to the lower bound of the ground state energy with a modest sum of squares. And it's very likely that there's many other applications of this. But I'll caution that this idea hasn't been employed in classical electronic structure or ground state energy estimation, and so it's likely there are places in the classical literature that this can work. So for example, there's a conjecture in a Matt Hastings paper that you can improve the sign problem in auxiliary field quantum Monte Carlo using these sum of squares representations appropriately. And so with that, I'm happy to take questions, and thank you for your attention.
Yeah, I can, OK.